Hi everyone, welcome back. In the last class, we have discussed blackbody radiation and many problems regarding that. Okay, and today we'll be discussing the second problem faced during 19th century, and that is photoelectric effect. Okay, and you must have heard a lot about photoelectric effect. So let's discuss from the very beginning to the complete end of photoelectric effect. Okay, so it is a direct confirmation for energy quantization of light. Okay, this photoelectric effect is a direct confirmation for the energy quantization of light. Okay, what is light? It is a wave. Okay, and in the last class we told that considering light or electromagnetic radiation as particle can solve many problems. Okay, this photoelectric effect is one such problem. Okay, so after dealing with this, we will understand that it is a direct confirmation for that quantization or that materialization of this radiation. Okay, so it was discovered by Heinrich Hertz in 1887. Okay, it was discovered by Heinrich Hertz. Okay, and what is the process of photoelectric effect? It is very simple. When light of sufficient frequency falls on certain metallic surfaces, then electrons are ejected from the surface. Okay, electrons are ejected from the metal surface. This process is called photoelectric effect. Okay, when electromagnetic radiation of certain frequency falls on metallic surface, electrons are ejected from the metal surface. This process is called photoelectric effect. Okay, and unfortunately classical physics failed to explain this phenomenon. Okay, we'll deal with that later. And this phenomenon, this process was successfully explained by Einstein in 1905, and for that he received the Nobel Prize. Okay, so we'll discuss about the process in complete detail, and then we'll discuss why classical mechanics failed to explain that, and then we'll obtain Einstein's photoelectric equation. Okay, so as I said, when radiation falls on metal surface, electrons are ejected. Okay, and there are certain observations. Okay, for this process there are certain observations they obtained. So first among them was, there is a minimum frequency. There is a minimum frequency for the incident radiation for the process to happen. Okay, in order to release or in order to eject an electron from the metal surface, the incident radiation should have a threshold frequency. Okay, radiation without having threshold frequency or the minimum frequency will not make any ejection of electrons. Okay, this is the first observation. Okay, and this threshold frequency is a material dependent property. It will be different for different materials. Okay, so it is a material property. Okay, if it is an iron piece, then the threshold frequency will be having some value, and if it is some lead, it will be having a different value. For aluminum, it will be different. Okay, so this threshold frequency is a material property. It is the property of the metal. Okay, now second observation is that the kinetic energy of the ejected electron is directly proportional to the frequency. Okay, suppose there is a light having threshold frequency, then electrons will be ejected. Okay, if we increase the frequency of the incident radiation, then the energy, kinetic energy of the electron will increase. That is the another observation. And kinetic energy is not dependent on the intensity of the radiation. Okay, if we increase the intensity, that doesn't change any that does not make any change in the kinetic energy. Okay, even if we change the intensity, kinetic energy of the electron is not changed. That is another observation. Okay, so in short, kinetic energy is proportional to frequency and is not dependent of the intensity of the radiation. Okay, and another observation is that if we increase the intensity, then the number of ejected electrons will increase, or in fact intensity is proportional to the number of photoelectrons. Okay, that is another observation. Okay, so these are the observations. And based on this, classical physics tried to make an explanation for this, but it was a complete failure. Okay, and why classical physics failed? Okay, according to classical physics, there is no such thing called threshold frequency. Okay, what is threshold frequency? Minimum frequency required by the incident wave. Okay, so according to classical physics, there is no such thing called threshold frequency. Okay, if we incident a weak radiation, okay, if we make a weak radiation to fall on the surface, then according to classical physics, the electrons in the metal will try to accumulate the energy from the radiation. I am telling this about classical physics. According to classical physics, even if we use a weak radiation, then as per classical physics, electrons should be emitted. Okay, but this is not actually happening. Okay, so how did classical mechanics explain that? If a weak radiation falls on the surface, then the electron will gradually accumulate the energy from radiation. Okay, and after getting enough energy, the electron will escape from the metal surface. This is the explanation from classical mechanics, but it is not actually happening. Okay, so that is the principle of gradual accumulation is from classical physics, and in order to verify this, people conducted experiments using weak radiations. Okay, so they incident weak radiation to a metallic surface for hours. Okay, for many hours they try to expose this metal surface with weak radiation, but even if they waited for days, nothing happened. No electrons were ejected. But when the frequency is having threshold frequency, or if the radiation used is having minimum frequency, then immediately the ejection starts. Okay, that is the observation. Okay, so even if the intensity is very low, if the radiation is having threshold frequency, then the electron will be ejected. That is the observation. Okay, and another important observation about photoelectric effect is that it is an instantaneous process. Okay, it is an instantaneous process. That means there is no time lag between incidence of radiation and ejection of electron. Okay, as soon as the radiation hits the metal surface, electrons are ejected. Okay, if the radiation is having threshold frequency, as soon as the radiation hits the metal surface, electrons are ejected. There is no time lag. Okay, and then classical physics is a failure in this context also. Okay, so there is no time lag. Okay, according to classical physics, if we use a weak radiation, then the electron will gradually accumulate energy, or it will save energy from the weak radiation step by step, and after getting enough energy, it will be released. Okay, if that is the case, there will be a time lag between incidence of radiation and ejection of electron. Okay, the electron will have to wait enough time to get the complete energy. Okay, and this is not happening. It is a spontaneous process. Okay, a fast process. Okay, there is no time lag. Okay, the radiation will come, electron will eject. Okay, there is no time lag. Okay, that is the observation. So classical mechanics was a failure, or classical physics was a failure to explain photoelectric effect. Okay, now let us discuss about Einstein's photoelectric equation. Okay, when classical physics failed to explain photoelectric effects, Einstein came to explain this effect. Okay, Einstein was inspired by Planck's quantization principle. Okay, yesterday we told what is Planck's quantization principle. According to him, energy contained by electromagnetic radiation is an integral multiple of h nu. Okay, nu is the frequency of the radiation. Okay, so Einstein told that electromagnetic radiation actually contain small packets of energy called photons. Okay, small packets of energy called photons. Okay, so he treated microscopically electromagnetic wave is no more a wave, it is a group of particles. Okay, and light actually contains many number of particles. Okay, these many number of particles are called photons. Okay, and each of these photon has an energy E is equal to h nu. okay, where nu is the frequency of the electromagnetic radiation. Okay, so this E equal to h nu is the energy of the incident radiation. Okay, and it's a simple explanation. Okay, and how he explained that is the incident energy is utilized to eject, to free the electron from the metal surface. Okay, for that some energy is required. Okay, that energy is called work function. That is called photoelectric work function. Okay, and we can represent that by W0. In some textbook, it is represented by phi 0. Okay, we'll stick to W0. Okay, so what is W0? The work done to release the electron, just eject the electron from the metal surface, or minimum energy of the incident radiation to eject the electron from the metal surface is called photoelectric work function. Okay, and we know that the minimum frequency is nu 0. Okay, threshold frequency is nu 0. Okay, so from this we can obtain a formula for work function. What will be W0? It will be h nu 0. Okay, so h nu 0 is the work function, which is the minimum energy required by the incident radiation to just eject the electron. Okay, just eject means with zero kinetic energy. Okay, okay, that is called threshold energy. Okay, or we can say that it will be the energy corresponding to threshold frequency. Okay, threshold frequency is nu 0. The energy corresponding to threshold frequency is called work function. Okay, or threshold energy. Okay, that's it. So the incident radiation is having an energy h nu. Okay, out of this W0 energy or work function, energy equivalent to the work function, is used to free the electron from the metal surface. Okay, and the remaining energy will be given as the kinetic energy of the ejected electron. Okay, so according to law of conservation of energy, the incident radiation has an energy h nu. Okay, out of this W0 energy is used to free the electron from the metal surface. Okay, and the remaining energy is given as the kinetic energy of the ejected electron. Okay, this is called Einstein's photoelectric equation. Okay, it's a simple explanation. Okay, so this simple explanation was possible only after treating light as a particle, or light as a group of particles called photons. Okay, from this all these explanations can be made. Okay, we can justify threshold frequency, this threshold energy, and this kinetic energy proportionality, intensity, everything can be explained using this particular equation. Let's see how. Okay, so from this we can write h nu is equal to, what is W0? It is h nu 0. H nu 0 plus k. Okay, so what will be the kinetic energy? K will be equal to h nu minus h nu 0. Okay, so k is equal to h into nu minus nu 0. Okay, this is an expression for the maximum kinetic energy acquired by the ejected electron. Okay, it will be the maximum kinetic energy of the ejected electron. Okay, k equal to h into nu minus nu 0. What is nu? Frequency of the incident radiation. What is nu 0? It is the threshold frequency. Okay, that's it. Okay, now if a radiation is having frequency less than threshold frequency, okay, if nu is less than nu 0, okay, if nu is less than nu 0 means the frequency is less than threshold frequency. Okay, then we can say that kinetic energy is equal to h into nu minus nu 0. Okay, if nu is less than nu 0, then kinetic energy will be having a negative value. Okay, this is not possible. Okay, so ejection will not happen when the frequency is less than threshold frequency. Clear? Now, what if nu equal to nu 0? What if nu equal to nu 0? Then k equal to h into nu minus nu 0. If nu equal to nu 0, k equal to 0. Okay, then at threshold frequency. Okay, nu equal to nu zero means at threshold frequency the electron will be ejected with zero kinetic energy. Okay, this is the metal surface and it will be just freed. Okay, it will be just released from the metal surface without having any kinetic energy. Okay, this is the simplest explanation for that. Okay, and from this expression, from this particular expression, it is clear that the kinetic energy is proportional to nu, right? Because nu zero is fixed. Okay, it is having a fixed value for a given metal surface. Okay, for example, if you are using lead surface, okay, if you are using lead, then threshold frequency will be having a fixed value, or threshold energy will be having a fixed value. Okay, then I can write kinetic energy is proportional to nu. Okay, so this is also justified. Okay, this is hidden in this equation, kinetic energy proportional to nu. Now we have to answer this question, why the intensity increases the number of ejected electrons. I told that when the intensity is increased, number of electrons ejected are increased. Okay, I can explain that. Okay, so this is the metal surface. Okay, this is the radiation. Okay, if we increase the intensity means number of radiations per unit area. Okay, intensity means number of radiations per unit area. Then the number of radiations will be increased. Okay, number of radiation is increased means number of photons is increased. Okay, number of photons is increased. Okay, each photon is having an energy h nu. Okay, this photon, suppose this photon has an energy h nu. Okay, this will eject an electron. Okay, and there will be another photon, this will eject another electron. Okay, and each photon will increase 1 electrons each. Okay, so if we increase the intensity, then the number of photons will be increased. Okay, number of photons will be increased. When the number of photons is increased, then the ejected electrons will be increased. That is how this thing is justified. Okay, so that is a detailed explanation for his that is an explanation from Einstein for this photoelectric effect. Okay, now there is one more thing, experimental setup of photoelectric effect. Okay, experimental setup of photoelectric effect. Okay, it is an evacuated glass tube. Okay, this is an evacuated glass tube and there is an metal surface. Okay, this is the metal surface. Okay, and this is glass. Okay, this is made of glass tube. Okay, and radiations are incident on this material. Okay, radiation will be incident on this material. Okay, and from this material electrons will be ejected. Okay, electrons will be ejected and we place two metallic plates here. Okay, like this, we place a metallic plate here. Okay, and some voltage V is applied across this plates. Okay, these are the two electrodes and some voltage V is applied. Okay, so if I give this as negative and this as positive, means like this. Okay, and I am giving an ammeter to measure the current. Okay, so this is some potential difference is applied here and this metallic surface is having negative terminal and this is positive terminal. Okay, so when the radiation falls, electrons will be ejected. Okay, and since this is negative, electrons will be repelled from this. Okay, so electrons will be moving forward in this direction and it will be reaching this particular collector. Okay, this is collector. Okay, so this will be emitter. Okay, electron emitter. Okay, so electrons will move towards the collector. Okay, when electron pass through this, then the current will be increased. Okay, this current is called photoelectric current. Okay, the current produced due to ejection of photoelectrons. The ejected electrons are called photoelectron. Okay, the current due to that electrons is called photoelectric current. Okay, that is the case. Okay, Now we have to obtain an expression for the maximum kinetic energy. How we can experimentally verify the maximum kinetic energy of the electrons? Okay, we have to find that out. Okay, for that we are reversing the terminals. Okay, we are reversing the terminals of the setup. Okay, so initially this is the metal surface or emitter. Okay, radiation is incident, electrons are ejected. Okay, this is negative terminal, this is positive terminal. Electrons will be repelled from this. So electrons will flow through the collector and that will increase the current. Okay, so from this we can determine the photoelectric current. Okay, now in order to find the maximum kinetic energy, we are reversing the terminal. Okay, we are reversing the terminal. Okay, reversing the terminal means we are giving this positive energy. Okay, and this negative energy. Okay, so this will be negative and this will be positive. Okay, so when light radiation falls, and this is a variable voltage source, this is a variable voltage source. Okay, when light or radiation falls on this, electrons will be ejected. Okay, so this will be having a frequency nu and an energy h nu. Okay, because of this energy, these electrons will be having some kinetic energy. Okay, the electrons will be moving with some kinetic energy. Okay, but we have applied a negative potential here. Okay, we have applied a negative potential here. We have reversed the potential. Okay, so the electrons cannot reach the plate. Okay, the electrons cannot reach the plate. However, energetic electrons can go to some distance. Okay, some electrons will be having high energy so that they will cross this barrier and reach this point. Okay, so what we'll do, we will increase the potential. Okay, we will increase the reverse voltage. Okay, so by increasing the reverse voltage, that faster moving electrons will be slowed down again. Okay, at some potential Vs called stopping potential. What is this? Stopping potential. At a potential called Vs, which is stopping potential, no electrons will be allowed to reach the collector. Okay, if we increase the reverse voltage at a particular value Vs, no electrons can reach the collector. Okay, that potential is called stopping potential. Okay, at that point the ammeter reading will be 0. That means photoelectric current will be 0. Okay, so I can explain what is stopping potential again. Okay, the point at which the ammeter reading or the photoelectric current becomes 0 is called stopping potential. Okay, the potential at which the photoelectric current becomes 0 is called stopping potential. Okay, now we can do a simple mathematics. When a charged particle having charge Q is placed in a potential V, it will attain a kinetic energy Q times V. Okay, this is a basic equation. When a charged particle having charge Q and potential is placed in a potential V, then the kinetic energy achieved by the charged particle is K equal to Q into V. Okay, so what is the charged particle here? It is electron. So in this case, the charge is E. Okay, and at stopping potential, what is happening? At stopping potential, no electrons will be ejected. That means the fastest moving electron will be stopped from reaching the collector, and that will be the maximum kinetic energy. That means K max will be equal to Q mix E, okay, into Vs. This is the expression for maximum kinetic energy. Okay, is that clear? Okay, so this reverse potential is trying to stop the electron. Okay, electrons are moving from this plate to this plate. Okay, so Vs is trying to, or V, this potential V is trying to stop the electron. However, energetic electrons will move across the barrier and they forcefully reach here. Okay, so we will increase V. Okay, when the potential is Vs, the maximum energy, the electrons having maximum kinetic energy will be stopped. Okay, at a particular point Vs, the electrons having maximum kinetic energy will be forced to stop. So that potential is called K max equal to E into Vs. From this equation, we can calculate the maximum kinetic energy. Okay, I think this is clear. This is the simplest explanation for this experimental setup. Okay, so initially it will be this negative and this positive. Okay, in order to find the maximum kinetic energy, we can reverse the potential. Okay, so this is Einstein's photoelectric equation, and it explains threshold frequency, dependence of kinetic energy on frequency, dependence of intensity on the number of electrons, etc. Okay, and this is the experimental setup, and this is the expression for maximum kinetic energy in terms of the potential applied. Clear? So that's all for today, and this is the theory of photoelectric effect. In the next class, we will be discussing about the problems in detail. Okay, see you in the next class. Thank you all.